Okay, we're going to talk about how we can use auto-differentiation to train our neural networks. So this lecture is called Neural Networks with Auto-Differentiation. The goal is to see how AD can be used to implement backprop for neural networks. Okay, so optimization using auto-differentiation. Now that we know how to do auto-differentiation, how do we do optimization with auto-differentiation? Consider a scalar function e that depends, and maybe depends remotely, on some variable v. So, and suppose we want to minimize e with respect to v. So we could be looking at this problem here. Minimize, let me rewrite that. Minimize e of v with respect to v. Now the computation graph for something like this, using this sort of notation I was using before, is we've got this node E here, and it points down to what it depends on. And it might depend on v immediately, or the v might be some other variable that's buried deep in a bunch of functions. But eventually, somewhere down there, there's a v. And so what we want to do is minimize e with respect to v. And to do that, we're going to use gradient descent. So we want v to be replaced by, or updated by, v minus kappa times the gradient, let me rewrite that, the gradient with respect to v of e of v. And so to do that, we're going to need this gradient here. Okay, so we've played with these sort of computational graphs before, and we've computed those gradients using chain rule. So let's, instead of doing it ourselves, let's now look at how we can use auto-differentiation with chain rule to produce those gradients. So first of all, the pseudocode for gradient descent using auto-differentiation looks like this. First, we initialize a possible solution, v, and we have to choose some learning rate or a step size, kappa. Then we construct an expression graph for e. Construct an expression graph for e. Now we loop. And what we do in this loop is we compute the gradient of e, and then we adjust v in that direction. So in this loop, first thing we have to do is evaluate e. At our current best guess v. Now what we're going to do is we're going to set the gradients in our data structure of v to 0. Okay, so set gradients to 0. So in other words, we want v.grad to be 0. Now v.grad, remember, that's our term for this. Now what we do, once all those gradients are 0, we can propagate our error back down through our computational graph. So propagate derivatives down. And in doing so, we increment v.grad. And now we use that gradient to increment v itself. V gets v minus kappa times v.grad. That's the gradient step. So that's the pseudocode. For neural learning, we use the same process to implement error backpropagation for neural networks, and we optimize with respect to the connection weights and biases. So instead of v, our e, our cost function, depends on all the weights and biases. So to accomplish this, our network will be composed of a series of layers, each layer transforming the data from the layer below it and culminating in a scalar valued cost function at the top. So that's an important part of this whole process, is you need to be able to measure the quality of your model as a scalar function. Okay, so there are going to be two types of operations. Remember, it's basically a sequence of operations from the input to the output. One type of operation that we're typically going to use is multiplying by a set of connection weights. Move over here. Multiply by connection weights. And I'm going to include adding bias as well. So adding a bias can be implemented by multiplying by connection weights. I'll just skip over the biasing. I think I have an exercise for you to implement the bias stuff. One of the types of operations is multiplying by connection weights. The other is applying an activation function. Apply activation function. Okay, so finally, after these connection weights, activation functions interleaved, the output of the network gets fed into a cost function that returns a scalar. Okay, so consider this very small network. Has input X. That feeds into this gray region, which the gray region sort of represents for that given layer the input current. Now going from the input current to this outlined box here is the activation function, which I'll call A in this case. Okay, so even within the layer, going from the input current to the activation is the activation function. Then we go through the connection weights, and I'll call this B. That's another operation called B. And then going from the input current to the layer, I'm going to call that C. And then finally, once we have that output, we compare it to our targets T, and I'm going to use the function D to represent that cost. So if we're given a data set X and T, how do we set up this computation? How do we compute or model this neural network? So first thing I'm going to say is A is the identity. It doesn't have to be. I'm going to make that small I identity. It's identity function. Just because it's the input layer, but I could just as easily have made it something else. But for this example, it's going to be the identity. B is going to be multiplying by some connection weights. So B will be, and I'm going to use lambda notation here. Lambda, which just means this is a function that takes an input Z and outputs Z times connection weights W. Okay, so this is multiply by W. C is going to be logistic, right? So this, the activation function for that second layer, I'm saying is logistic. And then finally, the D is the cost function. And I'll just call that function cost. So over on the left here, A, B, C, and D, these are all functions that transform their input. Okay, so now as a computational graph, I could draw it like this. I've got X coming in, and it transforms from A to some value. I'm going to make that a bit smaller. To A. Then A gets transformed using, that value gets transformed using B to some other value, which gets transformed by C to get some other value. And now that value combines with the targets T through some cost function D to get this final value. Okay, that's the computational graph. Now, each layer can be called like a function. So like I remember I said, the network is basically a sequence of operations. And so we can actually implement or compute the forward projection of the data through the network as a bunch of nested functions. So we can do it this way. Let's say little x equals a of big X. So that's taking our input from our data set and just running it through a. In this case, it's the identity function. So for example, a of x equals x because it's the identity function. Now z, let me put little x in here. Z then is going to be the next layer, so or the next intermediate value in this sequence of computations. Z is going to be b of little x, right? So the output from the a function becomes the input to the b function. Then the output from the b function becomes the input to the c function. And we're going to call its result y. So y equals c of z. So in this case, c of z equals sigma of z, so this logistic function. B of x was x times the connection weights w. Finally, E down here at the bottom of our computational graph is the function d given y and the target's t. So for example, d of y and t could be the expected mean squared error, or the expected squared error. As an example. Okay. So, but I want to point out that at each time, the output from one network becomes the input to the network, the output from one layer becomes the input to the layer above it. Okay? So each layer, including the cost function, is just a function in a nested mathematical expression. So the whole thing up there I can actually rewrite as E equals d of c. So what's the first argument of the d? It's the y, right? Where does y come from? It's c of z. What is z? Z is b of a of our input x. So I think I've got all my brackets there. So it's just it's a nested mathematical expression. So given that, our neural learning by gradient descent, remember, is basically updating our connection weights. I'm not good at doing arrows pointing to the left. W minus kappa times the gradient with respect to w of E. Now, where is w in all of this? Remember, w is part of the b function in this case. It's neither here nor there. I'm just sort of pointing that out at this point. We construct our network using objects from our auto-differentiation classes. We talked about a class called variables and a class called operations. Those are the two different pieces to these computational graphs. Here, I've got these A's, B's, C's, and D's, and I've got the X, Z, Y, and E. X, Z, Y, and E would be the variables, and A, B, C, and D are the operations. Okay, so the network is basically a sequence of operations. So I can say net equals, so I'm just going to use kind of non-programming language here. I'm going to call it A, B, C. Those are the three different operations that are performed on the input, and in that order, actually, going from left to right. And then our output, y, is net of x. So, which I'm imagining is C of B of A of x. And then after we've computed that, our error, or our cost, is basically the difference between the output of our network and the target. So this stuff here is what we call the forward pass, which sets the state of the network. So what I mean by the state of the network is that all the activations and input currents take on a particular value. You give an input, and that feeds up through the network, and all those input currents and neural activations have actual values that correspond to that input, and therefore correspond to that output and the error. And so we're going to use those states when we propagate the gradients down. So after we've done this forward pass to set the state of the network, we can take a gradient step. Now what we do is we set the gradients to 0, and there's a function called 0 grad for that, with no arguments. And then we call E dot backward. Again, well, it can have no argument. It technically has an argument, but there's a default value. Okay, now this is the backward pass, which sets all the gradients. Now it sets the gradients for that particular network state that it was in before. So you do forward pass, 0 the gradients, and then a backwards pass to set the gradients, the corresponding gradients. So here's pseudocode for neural learning using automatic differentiation. So we're given a data set, which I'll represent as inputs x and targets t, and a network model, which I'll call net, and I'll say it has parameters theta. That will be all the connection weights and biases, and a cost function, which I'll call simply cost. Then, once that's all set up, we run through a bunch of epochs. Each epoch is running through the entire data set once and adding up the gradient, or basically computing the gradient of the expected cost over the data set. Okay, so y equals net x. We already talked about what net x means. It's a nested set of functions. You can imagine that being in a loop. You could also imagine it being just one function calling the next function, and so on. Okay, once we have our output, we can get our loss. Loss equals the cost. By loss, I mean just the cost, obviously. Okay, now this is the feed forward pass that sets the network state. Now we work on the backwards pass to send the gradients down. So we say loss dot backward. No, first we say loss dot 0 grad. I was just seeing if you were paying attention. Then we call backwards, or backward. Okay, so this is the backprop pass. And then finally, since theta is one of the, I mean, there are many different variables that are involved in the computational graph of this model, of this network. So we could be computing the gradients with respect to all of those. What we really care about is the gradients with respect to theta, the connection weights and biases. So when we do the backward, it'll set all those gradients. But what we do and what we update is theta itself, theta minus kappa times theta dot grad. And this is that gradient descent step. Okay. Now it's time for a joke. Two clowns are eating a cannibal. One turns to the other and says, "I think we got this joke wrong." Okay, now let's look at how we can change this to work with matrices, because a neural network will have lots of matrix types of operations. So to work with neural networks, our auto-differentiation library will have to deal with matrix operations. So for example, let's talk about matrix addition. Suppose our scalar function that is the output of our network, or the cost function of our network, depends on some matrix sum addition. So we've got some cost function L, let me put over here, L, which depends on a bunch of things, including A and B and some other stuff. So let's let A and B be M by N matrices. This thing's trying to drive me nuts. M by N matrices. Okay, now we can ask ourselves, what is the gradient of L with respect to A and B? Okay, so let's let Y be that sum. So somewhere L depends on Y and Y depends on A plus B. Okay, so notice that Y is also M by N in this case. Pretty soon we'll talk about matrix multiplication, where it's not all these matrices are the same size. For matrix addition, they all have to be the same size. Okay, now the gradient of L with respect to A, I'm going to write it as the gradient of L with respect to Y times the gradient of Y with respect to A. Now, just because I know how addition works, I know that it's a Hadamard matrix between these two different things. It's like the elements of these matrices don't mix at all when you add them. So taking the derivative is just like applying the chain rule to each element individually, in this case for matrix addition. Now this first part is the gradient that we're getting from L that involves things after A. So it's the gradient of L with respect to Y. We're going to call that S. Okay, so it doesn't matter what that is, but it's going from L down to Y. We're just going to call it S. And so we can rewrite this as S times a Hadamard, or Hadamard times a big matrix of ones. Now that's just for addition. I know that just like how when you have Y equals scalar A plus B, the derivative of Y with respect to A is 1. Okay. Now, notice that this product is the same shape as A. It's because L is a scalar function, so taking the gradient of the scalar with respect to every element in A, you should have the number of elements that you have should match the number of elements in A. So same shape as A. So what about B? Well, B is really just the same thing over again. The gradient of L with respect to B is the gradient of L with respect to Y, Hadamard times the gradient of Y with respect to B. Now again, this is S Hadamard times 1, a matrix of 1s, that's M by N. And now this is the same shape as B because it's a gradient of some scalar with respect to the elements of B. Okay, so the fact that a and b and y are all the same dimensions is just a coincidence in this case because we're doing addition, but you'll see in the matrix multiplication down below that's not the case. Okay, so now in implementing this backward function, remember the backward function receives the gradient of stuff with respect to the output of this operation, the y, you could say, and then it passes, it adds its contribution to the chain rule, and then passes the buck down to the a and b in this case, to the variables that it depends on. So an implementation of backwards could look like this. Now this is just pseudocode. So plus is the operator, and the backward function takes an input s. Now s is the same shape as the output of the operation. Okay, so that's what you're inheriting down from above. Now you're going to call a backward. Now where are you going to send it? You're going to send it the gradient of L with respect to A. Or you're going to contribute that portion. Or you're going to contribute the element to the chain rule so that what you send down is the gradient with respect to A. So it's S Hadamard times a bunch of 1s. Okay, so same with B. We're sending down as an argument the gradient of L with respect to B. And other functions down below us in the computation graph will inherit that and add on their own element, their own terms or their own factors on the chain rule. Okay. Matrix multiplication. It's a bit more complicated. So again, let's talk about some scalar function L, which depends on A and B, but it depends on their product. So let's let A be an M by N matrix, and let B be an N by K matrix. Okay, so that their inner dimensions match so that the multiplication works. Okay, so again, let Y be A times B. So L depends on this Y, and Y is this product. So, and now remember, Y is M by K. So the gradient of L with respect to A will be the gradient of L with respect to Y times the gradient of Y with respect to A. Now not everything's the same size, so the matter, this is now matrix multiplication. So it pays to think a little bit about what the dimensions are here. Now the output Y, this gradient here, is the gradient of a scalar with respect to Y. So it's going to have the same shape as Y. It's going to be M times K. The gradient of Y with respect to A is going to be, it's going to contribute a factor that is K by N. Why? Because we need the result to be the same shape as A, which is M by N. Right? Okay, so that first part is S. It's the gradient of L with respect to Y is the gradient that we inherit. This is matrix multiplication, and the gradient of Y with respect to A is B transpose. Now, why that's the case, you can prove it to yourself. It takes a little bit of soul searching, but it works out. I mean, it kind of makes sense when you've got a quadratic function. If I said y equals a times b, and I wanted die y by die a, it would be b. It's but when you have a matrix, you have to transpose it. Okay, and then the gradient of L with respect to B is kind of the same story, except I'm going to swap the things. I'm going to say the gradient of Y with respect to B first, matrix multiply by gradient of L with respect to Y. So again, what we need is something in the shape of B, which is n by k. So we better have an n here and a k over here. So the gradient of L with respect to y needs to be the same shape as y, which is m by k. And so this had better be an m here. And it works out if it's just A transpose times S. Okay. Now, so the implementation then would be dot backward. So this dot here is just this dot here, just the name of the operator. And it brings in S, which is the die L, or gradient of L with respect to the output of this operation. And now it will call A dot backward, and it'll send the gradient down. So I'm not going to fill that in for you. And same with B. It'll send down its gradient. And for this, I'll say C assignment. You're welcome. So this is basically what you need now to apply a matrix type of library or module of automatic differentiation routines or classes, and apply them to neural networks. So the neural network is basically just, you can do neural learning, essentially do backprop, by constructing your network of a whole bunch of matrix variables and matrix operations, each of which has a backward function and knows how to contribute its derivative to a chain. So if you build your network out of these functions, it constructs the computation graph for you, and you can just call backward, and it'll go down through the graph to the data structure and populate all the gradients. And then you can pull out and use those gradients to do gradient descent, and therefore do error backpropagation by gradient descent.